Welcome back to Comp 1405. In this chapter, we'll discuss file input and output operations, as well as the notion of exception handling. With this, we'll be able to make programs with states that persist across separate executions, and help protect our program from entering into error states that lead to unexpected program crashing. Memory in a computer is organized in a hierarchy of different types. At the one end, you have a hard drive, and this is where you store things like your Python programs, your cat gifts, and all of your old pirated Game of Thrones episodes. Just kidding, stealing is wrong. Now, hard drive storage is plentiful, but comparatively slow. You can think of hard drives as the computer's long-term memory. Now, the nice thing about a hard drive storage is that it's persistent. So even when the power goes off, all that information stays stored on your computer. So when the power comes back on, when you rerun your programs, all that information is still there. The image here is of a hard disk drive. This is the format that gave us the common term hard drive to this day. Even though the solid-state devices are more common now, both types still function as the computer's storage. Next to the hard drive is memory that's commonly known as the computer's RAM. Now, RAM stands for Random Access Memory, which is a term that's maybe a bit outdated now, given that solid-state devices implement random access as well. But the name was to distinguish from hard disk and floppy disk memory, which both had spinning disks and a reader that had to be physically moved into place in order to read the correct sector. By contrast, RAM memory can address any specific sector in a single operation. RAM functions as the computer's main memory buffer. This is for holding things that it's not actively working on directly in the CPU's memory registers. RAM's generally faster than hard drives, so it's often less abundant and more expensive. But this is where your programs are loaded, and the program's call stack and heap are both stored. This kind of memory is volatile, though. You can think of it as trapping a very small electrical current inside a loop, which means when the power goes out, that memory disappears, and the information along with it. This means RAM is like your computer's short-term memory. There's another type of memory known as registers, and this is the computer's active attention. These are very small but very fast memory locations that are built directly into the CPU itself, and the CPU uses these registers while performing the basic operations that it does. These days, memory continues to evolve as GPU memory takes on greater importance and unified memory seeks to merge the two, which is to say, please consider all of these descriptions as somewhat approximate. What's important to note here is that our programs run on memory that disappears. If we want our program's state to persist, we'll have to write it to the hard drive instead. Now, before we learn how to store files to the hard drive in Python, let's first talk briefly about files, file systems, and paths. Now, we touched on this a bit at the beginning of the course, and you probably had to explore these concepts on your own quite a bit while working with the course material. But let me just quickly review the notions of files, file systems, and paths to make sure everyone's on the same page before we move on to using files in Python. So files are individual units of data which are stored on the hard drive. So if I said program.py or cat.gif, these are individual entities of data. Now, files are grouped into directories, sometimes known as folders, but directories can contain other directories, which leads to this tree-like structure. So your entire hard drive is organized into a tree of directories called the file system. Without the file system, there'd just be one long list of data, and to find anything, you just have to check all of it. With the file system in place, we can use our directories to sort our information into this structure, and I can focus on one subfolder instead of all of the others. So the top of the file system tree is what's known as the root. In Windows, this is just the name of the hard drive, so C/. In Unix or Mac, this is just the /. And a path is the location of a file on your system. So a path is a walk from the root down to a specific file or directory. So for example, if I open a PowerShell window in the current chapter's code folder, the prompt from PowerShell tells me the path to that current folder. So notice at one end of the path is the root, and then it's just a sequence of folders that are a single path through some large directory tree that ends at the current directory. If I wanted, I could change to the root by saying cd to change directory, and then /, and that takes me to the root of my file system. And if I wanted to get back to the folder where I was, I could say cd and then type out that whole path, c:/users/me/ ... As a shortcut to doing all this, note that if you have the folder open in your File Explorer, it has a path line here at the top, and if you click on it, it gives you the exact path text. You can just copy that, and then in your terminal say cd space, and then right-click to paste, and right-clicking gives me all of that. So I can say enter, and now I'm back in the directory where I started. Almost. There we go. So the PowerShell prompt tells me the current working directory, as it's called. And notice that each directory is separated by a slash. Now, in Unix and Mac, they'll use a /. In Windows, it uses a \. And this wouldn't be an issue, except when we're talking about Python, recall that backslashes mean escape characters. So for example, if I open up a Python terminal and said print some path, /new folder \temp. So if I wanted to print out this path, notice it does not print out the path as I expected. It takes /n and /t as meaning new line and tab respectively, and the whole thing gets a bit garbled. The solution to this, if you're coding in Python in Windows, is to just use // anyways. Windows is cool with it. Another alternative is to say double \, so \/, and that works. Alternatively, we could say front slashes, and that works as well. Now there's also two different ways you can specify a path. There's what's known as absolute paths, which start at the root and walk all the way down to the target directory or file. And then there are paths known as relative paths, which start at the current working directory, wherever that happens to be, and walk up or down to the current target. So we saw, for example, an absolute path in all of our terminal prompts. And if I wanted to change directory, I did so by saying cd from C users all the way up to the current folder. And then I saw a relative path. For example, I just said cd code. So because I was already in this directory and it had a file or a directory called code, then it changed into that without needing to specify all of the steps above that in the path. So relative and absolute paths, both are useful in Python. And lastly, when working with paths, you're likely to see the single dot or double dot operators. A double dot operator means go up one level. So if I said .. /, that refers to the directory above the current one. So that'd be, in this case, chapter 8 file IO. So if I said, for example, cd .. Notice my working directory has removed the /code from the end of my prompt, meaning I've gone up one stage. If I were to say cd .. and then say chapter 7, whatever's there. So it goes up one level and then it switches to chapter 7, and now I'm in the chapter 7 folder. If I wanted to go back to where I was, I could say cd .. /8/code. And now I'm back to the place that I started. The single dot is perhaps a little bit less useful. It means the current location. So if I were to say cd and then a single dot, it's an acceptable command, but notice nothing changes. Literally that says change the directory to the current directory, i.e. do nothing. It is somewhat nice, for example, if I wanted to be explicit about using a relative path. So if I were up a folder, for example, and I wanted to say change into the code folder, I could say cd .. /code. Means the same as saying cd code, but it means specifically cd start from where I am /code, which is assumed, but again, being explicit sometimes helps with clarity. All right, with all that in mind, we now understand the basics of file systems. So now let's turn our attention to learning how to use files in Python. So the most basic and prerequisite operation that you can do to a file in Python is to open that file. Without opening the file, there's nothing else we can do with that file. Opening creates a link between Python and the file itself. To do this, we can use the built-in function open. So we just say open, then the name of our file, and then we pass in some string representing the mode. So the three main types of modes are reading, writing, and appending, and we'll discuss each of these in turn. If you do not include the mode parameter, it's an optional parameter, its default value is reading. If we'd like to submit a mode parameter, it's just the letter R for reading, the letter W for writing, or the letter A for appending. There are additional options for managing reading and writing simultaneously or dealing with bit strings, but we're not going to touch on those in this course. But know that the open function allows for a bit more operation than we're demonstrating here. The file name parameter is a string indicating the path, either absolute or relative, to some file in our system. The file name parameter is just a string which indicates the path, either absolute or relative, to the file that we're searching for. If it's a relative path, it's relative to the current working directory. So that's the directory that you're sitting in when you type Python to the terminal. Note, if you don't run Python from the terminal, that is to say, if you're using the IDE's run button, this might be different. You'll have to look into the IDE's settings in order to change the current working directory. In these videos, I'll always run Python from the terminal, which avoids this confusion. So if your Python program, your .py file, is stored together in the same directory as some, say, text file, then all we have to do is say file equals open, then the name of that file, and that's it. And that will create a file link in Python that lets us access that file. So in VS Code, I can make a new file. Just go to the directory that I'm currently in, click on the new file button. I'll call this mydata.txt. This is just a blank text file. I can put any data in here. I'll say line 1, line 2, line 3, just so we have some content in there. And then I'll make a Python file. So in the same folder, I will say file io demo.py. Notice Python files, they're also just plain text files that happen to have the extension py, but they are just plain text in the same way as the other file. So I've got a new Python file. So let's create a quick function. So I'll say def open file demo. And all this will do is open up our file. So we'll say f equals open, and then the name of our data file. So mydata.txt. Notice that's a string. And then if we want, we can include the mode as well. If I left this off, if I just typed in mydata.txt, it would assume read mode, but we can be explicit and include the letter R to say open this file to be read. Now we haven't covered how to read, but we'll get to that soon. So once we have that, let's see what this gives us. What's this variable f containing? So let's just print the variable f. And when we're done, it's important that we close this file. So we'll say f.close. Let's make a main file here. So def main. And that's just going to run open file demo for now. Okay, so let's see how this works. We will say python file demo.py, and this runs. And the thing that printed out, so on line 3 here where we printed f has the value io text wrapper, which has a file name mydata, a mode for read, and an encoding, which tells Python how to read the 1s and 0s that are stored in that file as characters. So you can think of this like the ASCII encoding, but a bit more advanced to involve all the special characters that don't fit into ASCII. So we open the file, we got this text.io wrapper thing. We'll see how to use that to read our file in just a second, but I want to show another demo of opening a file, one that's not stored in the same location. So if instead of storing the Python file and the text file directly next to each other in our directory structure, a lot of times you'll have a data folder, sometimes a data hierarchy of many folders that separate your data in different ways, or sometimes your data is stored completely separate from your file. In that case, you'll need to include a path to your file as well. So that path again is from the current working directory, which is told to us down here as fileio/code, which is the directory where all these files are stored. I can type ls to prove that. It has all the same files as you see in the VS Code Explorer here. But if, for example, my data wasn't stored directly next to my Python file, let's say it's just down one level into this data folder, then we can include a path when we're opening our file. So instead of just saying my data, I would say the data folder /my data. Or if we want to be very explicit, I could say / the data folder /my data. Note, if you say just /data without a dot in front of it, if you're using Mac or Unix, this means go to the root directory and look for a folder called data. So when talking about relative paths, make sure you say either / to say the current directory /something, or say neither, and it will presume that you're starting from the current working directory. I prefer being explicit, so I'll say / data /my data. So that says from the current directory, which is fileio/code, look for a folder called data, which it finds, and in that folder, then look for a file called mydata, and it finds that, and now it should open to read this just the same. Save and run our code. And we get the exact same thing, except notice now the file is stored somewhere slightly different. So now we know how to open and close files. It's important to close the file because closing closes the link between Python and the file. This frees up space in your program to do other things. It also flushes any of the operations that were happening on that file. That is to say, it makes sure any of the processes that were halfway complete get fully completed so that the file can be closed. In older languages, not including Python, if you don't close the file, you might end up with a memory leak. That is to say, that file can remain open even after your program exits. Python takes care of some of this for us, makes it a bit easier, but it's still a good idea to keep in mind that you should always close the file. Once we have our file open in Python, it's time to actually read the data. So to read the file, we need to have opened the file in read mode, which again is the default mode. It's important to note that if the file doesn't exist, then the program will crash as well. So if I said, for example, if I had forgotten this folder, I just said / my data, and tried to run this code, we get a file not found error, no such file or directory, because there's nothing in the same folder, because I said look at the current working directory and find a file named mydata.txt. There isn't one there in that directory. So because I gave it a bad path, there's an error. So assuming we've given it the correct path, then it's time to read our file. So there's 3 ways that we can read a file. Method 1 is to read all of the data into one big string. If I just say file.read, then it takes all the text in that file and stores it as one big string in the variable text here. So from the first line to the very end line, all is one big string. Method 2 is to read the file one line at a time. So if I say file.readLine, that will read the first line. If I put this into a loop, I can then read the second, the third, all the way up to the end of our file. Method 3 is to kind of combine those 2 things. We say file.readLines, which takes all of the file text and returns all of it at once, but it does so as a list of individual strings, where each individual item in that list is a single line from our file. All right, let's see these in practice. Let's go back to our Python. We'll make a new function here. So I'll say def display whole file. We'll pass in some file name. Now we can open that file. So I'll say my file equals open the file name. Assuming we're given a proper file name, we can just open it that way. And again, to be explicit, I'll include the read mode argument. On the next line here, we've opened the file. The next step is to read the file. If we want to read everything, we can just say text equals myfile.read. And that takes all the text from our file and stores it in this variable called text. Now that we've done reading it, we can say myfile.close, because we don't need that file anymore. And then let's just print what we have. Normally we do some processing on this string. In this case, we'll just print it out. And this should print everything. So let's make sure we're running this file. So I'll come down here, comment this out, and say display whole file. And I'll give it a file name from data sojokes.txt. So we'll say ./data/sojokes.txt. Save and run our code. And it prints out a whole bunch of jokes from our text file. Top to bottom is one big string. So to read a file, we just say myfile.read. That takes all the text in our file, stores it as one big string in text, at which point we can then close our file and operate on that string in the way that we've already learned. So doing all the finds and slices that we know how to do. The second method for reading a file is one line at a time. So we could say def display file by lines, which takes in a file name. And we'll do the same thing. We'll say f equals open file name in read mode. Then instead of reading everything, we have to read one line at a time. So I'd say line equals f.readLine. So now line takes the first line from our file, and we can process that to say print or do whatever we want. So if we want to get all of the file this way, we have to then process this in a loop. So I can say while the line that I've read does not equal the empty string, that means we read something from our file, so we can continue to process. So I'll print that one out. I'll print out some characters in between just so we can see that this isn't doing the exact same thing. Say times 20. And then we'll grab the next line. So I'll say line equals f.readLine again. So notice we read the line once first, so we have our condition. We have a precondition loop here that says if the line we read was empty, then don't do anything. If it's not empty, then print it, print some other stuff, read the next line, and check if that one was empty. Eventually, we'll get to the bottom of the file, and so the line will be empty, and that will exit our function. Notice the entire time we're doing this, we're still reading from the file, so we leave the file open until we finally are done the loop. At that point, we can say f.close. Notice the open and close happen outside of the loop. If we are opening and closing inside the loop every time, that can be very costly. Reaching into an operating system, finding and constructing one of these file links can be very expensive, can be very time consuming from a process point of view. So it's a good idea to limit the number of times you open and close your files to just those times that are necessary. All right, so let's test this out. Come down here and we'll say display file by lines, and we'll take this same file. Save and run our code. Make this a bit bigger so we can see. And notice it printed every line in our file again, but in this time one line at a time. Notice how each line in our output is followed by a blank line. That's because when we print the line, print automatically includes a /n, but the line we're reading from the file has a /n as well. So when we're printing this out, we're printing out the line, which includes a /n, and then print adds a second /n. So that gives us the blank line after each line. Okay. So the third method for reading a file is to use the readLines function. And this returns all of the contents of the file as one big list, separated by line. So each individual line is a single string within that list. This is useful if we know that our input is already separated by lines, such as the SoJokes file. So if I said, for example, def tell joke, we use this function to tell us a random joke. So I'll import random. It's only going to be used in this one function. And this will tell a random joke from a joke file. So step one is to open the file. So I say file equals open same file. So ./data/sojokes.txt. Still opening in read mode. The next step is then to read all of the content. So I'll say lines equals file.readLines. Notice oddly, even though it's two separate words, they're both lowercased. It's an error to say read lines with a capital L. So just to make your attention aware, it's read lines lowercase l, similarly with read line as well. And once we've read all the lines, we can say file.close, because now we're done with that file. We have all the content from the file, we don't need the link anymore. Once we've done this, we now have a list that contains a bunch of strings, and we can operate on this in the same way we've learned how to deal with lists and strings in previous chapters. So in this case, if I want to get a random string, I can say generate a random number. So r equals random.randRange, I'll say. RandRange is like randInt, except it doesn't include the last value. So it's inclusive of its first index and exclusive of its last, just like the range function, which makes it pretty useful for lists, because I can say something like randRange from 0 to the len of lines. So it says take a random index in that lines list, and we'll use that to just print out a joke. So I'll say print lines at r. Save. Let's make sure we're running the right function. So we'll say tell joke. And we run our code, and it tells us just one joke. How did the hipster burn his mouth? He ate pizza before it was cool. And notice we're getting a different random joke every time. Wonderful. So now we've learned how to read our files. We've learned how to open our files, we've learned how to read our files, and we've learned how to close them after we're done reading. This is useful if other people make files for us and we want to have our code process through those, which is a very common operation in programming. But file I/O is more useful once we've learned the O part of that, the output. So let's learn next how to write to files. So to write to a file, the first thing we need to do is open that file again, but now instead of opening in read mode, we'll open in write mode. And this is a mode that lets the system know that we're going to be adding information into that file rather than extracting information from it. So to open a file for write mode, we do the same thing, file equals open, the name of our file, and then instead of including an R for the mode, we include a W for the mode. Now if that file doesn't exist, it will be created where we went to access it. If it does exist, it will be destroyed and a new file will be put there. So if it does exist, it's being replaced, so be very careful with that. So let's see this in practice. I return to Python. I can make a function def write numbers that opens a file for write mode. In this case, we'll just write a bunch of numbers to see how write mode works. So we'll say f equals open. I'll make a new file that doesn't exist, output.txt. Notice that's not a file that exists anywhere in my directory structure here. And then in order to make this in write mode, I just include a W instead of an R. So that opens some file with the variable called f, and now we can write into that file. So I can say for I in range, say 0 to 25, f.write, so we use the function write to write into our files. Works a lot like print, and we can just say str of I. At that point, we've done all the writing we want to do, so it's a good idea to close, f.close. And let's try it out. So we'll come to the bottom here, we'll say write numbers. Run our function. And nothing happens here, because remember this function didn't print anything. Now it's all writing to some file. And if we look down our Explorer window, we see there's a new file here called output.txt. If I just open this up on the side, we get all our numbers. 0, 1, 2, 3, 4, 9, 10, 11, 12. So a few things to note here. First off is when I was writing this, I had to say the string of I. The file write function expects a string argument. If you include numbers, it's an error. So for whatever value you want to write, make sure you're converting it to a string first. Second thing to notice is that unlike print, the write function doesn't add in new lines at the end of every print statement. So every time we say write, it's just writing exactly what we said. I said write 0, it wrote a 0. I said write 1, then it wrote a 1. I said write 2, and it wrote a 2. Okay? If I want to have these all on separate lines, I have to make sure I include the new line every time. Run our code and notice our file changed. So now we have all the numbers 0 through 24 on separate lines. I would like to also point out that the file.close function has more value than just closing the file. It also flushes the buffer before doing so. The idea here is that write operations to your hard drive are quite slow as compared to, say, working memory. So rather than constantly writing for each individual number, what the system will do is it will build up a buffer of all the write operations that need to happen, and then once that buffer reaches full, or once the file is closed, then it will take all of those operations and apply them. This just speeds things up in the background. There's nothing different about how your code needs to be run to understand this, but you should know that it's happening. To demonstrate, let's open up the Python REPL here. If I go Python, and I'll do the exact same steps that I did just before here. So let's make a new file here. I'll say f equals open, I call this output.txt, and I'll open this in write mode. Okay. Notice just by opening the file, it's cleared the file. So any of the previous data has already been destroyed because I said open that file in write mode. But now let's do some writes. So I'll say for I in range 25, f.write the string of I plus a new line character. So a few things to point out here. So we got a bunch of output, which is odd because we didn't say to print anything. This is just the value of this statement. It returns the number of characters that are written. So it returned 2 characters, 2 characters, 2 characters. So that's the number and a /n, the number and a /n. There's about 10 of those, and then we get 2 digits in the /n when we get to 2-digit numbers, 10, 11, 12. And then we get to the end of the loop. But notice nothing happened in our output file. We did all these write operations. We said f.write to our output.txt. We saw that it opened this file because it cleared that file, but nothing's actually been written into that file yet. So even though it's said it's done all of these write operations, because we haven't closed the file, the write buffer hasn't been flushed. There's 2 ways we can do this. There's actually an f.flush function that we can do if we want to manually flush. But if we just close the file, since we're done writing to it, that will also flush the buffer. So if I say f.close now, then all the data shows up. So that's writing to a file. And again, the thing that you really need to be aware of is if we're writing to an existing file, it will destroy that existing file, which isn't always the use case that you want. A lot of times you'll want to open an existing file and just change it a bit. So what we can do there is either open a file and read everything in so that all of the data is in our program, and then write the entire thing again, but with the changes that we want, or we can use what's known as append mode. So to open a file for appending mode, we use the append mode marker, which is A for append. Now the big difference between appending and writing is that if there is an existing file, rather than replacing it, we're going to open that file and put the cursor at the end of it. So when we start writing to it, we're going to extend the content of that file rather than obliterating them or replacing. As with writing mode, append mode will create non-existent files. So if I say open a file that doesn't exist, in append mode, we'll still get a brand new file, and the cursor will just be at the beginning of that file. And at that point, there's no difference between using append and write mode. But if the file does exist, that's where the difference comes in. We can demonstrate this in our REPL example. So I can say open that same file, so f equals open output.txt, and do this in append mode. And notice it didn't obliterate the file right away. The file's still there. And I can say something like f.write. I'll just say the number 25/n. So it wrote 3 characters, 2, 5, and the /n character. And then if I say f.close, then it pushes that to the file as well. Notice it didn't destroy everything. In this simple example, I wrote a single line, but we still have the previous 25 lines all there. And now we've added in 1 extra line.